Hi everyone, and welcome to this series of PEO exam question. And here we have the exam of electrical A6 power systems and machines. And here we have a three-phase question. I found this is very interesting question because it has almost everything that you need to know about three-phase systems. So let's go with start the question. So here it says a balanced Y-connected three-phase load. So this is the load, this is the Y-connected, and the impedance of the load is 17 angle of 62. Since the load is balanced, so each one have exactly the same impedance. It's connected to a balanced three-phase supply. So the phase supply is also in Y connection because it's a four-wire system, as you can see here, and the source is receiving the neutral, so it is a Y-connected supply as well. Between the two, we have here an impedance. ZL is equal to 0.1 plus J 0.3. Now, the voltage at the load, the line to line is 600 volts. So the voltage here between the line to line here is 600 volt. And then here we are asked to find different things in the circuit. We'll take it one at a time. Okay. Now, the best way to handle such a question when you are giving the configuration of the source and the load is to isolate one phase. Because working in a single phase is much easier than working in a three-phase system. Okay, so let's do this and start with the first requirement. It says find the line current from the source. So I need to find this line current, which is IA basically. This is the line current for IA. And the voltage at the source. I want to find also the voltage basically at the source. Okay, so I will isolate this phase. And I will go through the neutral. As I said, this becomes much easier to deal with. Okay, so now this will be my my new circuit. This will be my Z, and my Z is 17 angle of 62. I will have here the impedance, which is 0.1, and this is J 0.3, and this is what I call it my VAN, the voltage at the source, the phase voltage at the source. Now we are given the line voltage at the load, okay, but since we are working in a single phase, I need to find this voltage basically line to neutral. So the V, I will call it VAN capital. So this is AN. And this is small a n. So your VAN, the voltage across the load, is the 600 and divided by root 3, because in Y connection, the line to line voltage is root 3 times the phase voltage. We want to find the phase voltage, and I will use this as my reference. I have the right to choose any reference. If I'm not giving any specific angle of the voltages, then we can use the phase voltage as our reference, because this will make things much easier for us. And this will give me 346.4 angle of 0. Now I need to find this current IA. The line current from the supply is the same current that goes through to the load. So in Y connection, the line current and the phase current are exactly the same. So how to find this IA is very straightforward. You divide the voltage here that you have it across the load, which is the 346.4 angle of 0, Ohm's law, divided by the impedance of the load, 17 angle of 62, and this will give me an current 20.4 angle of minus 62 amps. So this is my current. And it says, what is the voltage at the source? We apply KVL. So your VAN is basically equal to the current IA times the 0.1 plus J 0.3, the impedance of the line, plus the voltage at the load, which is the 346 0.4 angle of 0. Substitute IA with its value 20.4 minus 62 times 0.1 plus J 0.3 plus 346.4 angle of 0. Now I am multiplying a polar with a rectangular. If your calculator cannot do that, then you have to convert this into polar, multiply, convert them to rectangular, add with the voltage and go back to polar. If you do all of this, you will find that the voltage VN is 352.84 angle of 0.18. Now that is the voltage, the phase voltage. If I want to find VAB, the line voltage, it's root 3 times 352.84 angle of 0.18, and you add to this plus 30. So that is the voltage at the source. This is the phase voltage, and this is the line voltage. Let's go to the second thing. What is the total average and reactive power of the Y-connected load? So we want to find for this Y load, what is the P and what is the Q? P is equal to root 3 V line I line cosine theta, which is the power factor, which is equal to root 3 V line I line cosine of theta V minus theta I. And here we have to be very careful because the angle that we have to use here, theta V and theta I, is the angle of the phase, the angle of the phase impedance. The phase quantities, the phase voltage and the phase current, which is basically the angle of the phase impedance, because Z of the phase, this Z, is equal to VAN, if we call this as AN, divided by the current that go through this, through I. A, this is will have theta V, and this is will have theta I. So this is equal to VAN divided by IA angle of theta V minus theta I. That is the power factor angle. Okay, so you have to be very careful that you have to use the phase quantities. So your load, P at the load, okay, so your P is equal to root 3. The voltage is 600, the line-to-line voltage. The line current is the same as the phase current, so the line current is equal to 20.4 cosine. The angle of the phase voltage is 0. The angle of the phase current minus 62, which is the angle of the impedance, as a matter of fact. And this will give me 9.953 kilowatt. Q, on the other hand, the same thing, but it's a sine. So it's root 3, 600 times 20.4 sine of 0 minus 62, and this will give me 18.72 kVAR. So that is the load, the real power and the reactive power and the load side. In part C, it says here, a three-phase induction motor is connected in parallel with this load. So I come here and I connect in parallel a three-phase induction motor. So we'll have here a motor that is a three-phase motor that is basically connected to in parallel with the load. The motor has an output 23 horsepower. This is the output. This is the mechanical output of the motor, and the efficiency is 83%, and the power factor is 0.85 lagging. We need to find the new line current now. Now I will have two line currents. This I will call it I line 1, and this is I line 2. Now this is I line 1 is the same that we calculated from the previous step. This is the current that the load is consuming. Now the I line 2, the current that goes through the motor, this is what I want to calculate. Adding these two, you will get now our new IA. Okay, so let's start for this. Okay, now we know the P out is equal to 23 horsepower times 746 to convert this to watt, and this will give me 17.16 kilowatt. Now the efficiency is actually P out over Pn, So your Pn is equal to your P out over the efficiency. It is 17.16 divided by the efficiency, that is 0.83, and this will give me 20.67 kilowatt. That is the input electrical power. This is how much power the motor is basically consuming. So from this, I can find IL2, or I of the motor. It's equal to the P, the 20.67 times 10 to power 3 is kilowatt, divided by root 3 times 600. And then the angle is minus cosine inverse of 0.85, because this is a 0.85 power factor lagging. So the current has to be minus, which makes sense because this is an inductive load. And I will get 19.9 angle of minus 31.8 amp. Now, this is basically the current that is driven or taken by the motor. So now my IA prime, or my IA new, the new line current, is equal to this current, that the 19.9 angle of minus 31.8 plus the current that is consumed by the load, which is the 20.4 angle of minus 62, and this will give me a total current equal to 38.9 angle of minus 47. So that is basically the new line current that is for the new system. Also find the average reactive power drawn by the induction motor. We already did that. This is how much the average power. Now the reactive power, the Q of the motor. Basically, we can use the power triangle to find this. So here we know P is 20.67 kilowatt. And this is your theta. Your Q is unknown. To me, this is the Q by the motor, okay? And theta, we already know it, which is the 31.8. So from this, that you can use tan of 31.8 is equal to Q of the motor divided by the 20.67 times 10 to the power 3. From this, your Q is equal to 20.67 times 10 to the power 3 times tan of 31.8, and this will give me 12.82 kVAR. This is the reactive power consumed by my motor. Then it's also asking for the voltage at the source with this. Now again, this is KVL. Now basically I will have a single phase circuit. Now I know the current here and I know the current there. I know the total current. I know the voltage here. So just a simple KVL for this. So your VAN is equal to the 346.4 angle of 0, the voltage here, plus the total current, which is 38.9 minus 47 times the line impedance, which is 0.1 plus j.3. And then do the calculations. You will find that basically the total voltage is 357.76 angle of 0.83. Now, if I want to find the VAB, again, root 3 times 357.76, and this is 0.83 plus 30. This is how we can find the new currents, the new power, total power, the power of the motor after connecting a new load in parallel. In part D, now we wish to correct the power factor of the loads. Now the two loads in parallel, we have certain power factor. We want to correct this to unity. What does it mean in unity? Unity means we want basically to have our total Q equal to 0. So what is the total Q here? Q total that we have it at the load is the summation of the Q from the load and from the motor, which is basically 18.72 plus 12.82, and this will give me 31.54 kVAR. So this is the total inductive reactive power coming from these two loads. I have to have a QC is equal to minus this to cancel completely, and I have basically a power factor equal to unity. So the absolute value of QC is equal to 31.54 kVAR, the same as the total reactive power, because this is, we want to have a power factor equal to unity. Now, if we have the capacitor bank connected in Y, what is the required phase impedance? Now, we need to find the C first, and then we can find the impedance. Let's find C first, and then find the impedance of the capacitor. Now, how to do that? Now, Q is equal to basically, as we know it, is equal to root 3 V line I line sine of theta. Now sine theta is equal to basically is equal to 1. Okay, and we can also convert the current in terms of the voltage, so we will end up having this formula that the Q is and the current with the voltage. So here basically this is your impedance, this is 1 over omega C, and this is your current I, and this is your voltage V. So the current is equal to the voltage divided by 1 over omega C, so it's equal to V times omega C. So this is your current, so I can substitute the current here. Then you will have the Q is equal to and if you take out the root 3, then this will be V squared times omega C. Now this will be equal, if we use the phase values, this will be root 3 times root 3, this will be actually 3. Okay, so Q is equal to 3 V squared omega times C. Now, so you can see that the C is equal to Q over 3 divided by V squared times omega. So Q over 3, this is the 31.54 times 10 to power 3 divided by 3. Divide by V square is basically the phase voltage, 600 divide by root 3 square, because now we use the phase quantities here. Okay, let me redo this just for your reference here on the side. Your Q is equal to 3 VI sine theta. Now for a pure capacitor, QC is equal to 3 V times I, and using Ohm's law, I is equal to basically VWC, so this is equal to 3 V squared times omega C. So that is what we have here. Okay, now the omega is basically 60 hertz system, so it is 2 pi f, which is 60. This is the standard in North America, and you will find this is equal to 13.9 millifarad. This is the capacitance C. If I want to find the basically the phase impedance, then it is 1 over omega C, which is equal to 1 over 2 pi 60 times 13.9 times 10 to minus 3. And this will basically give me an impedance equal to 0.19 ohm. So that is your part D, how to find the impedance. Finally, what is the new line current? Okay, now the two loads together along with the capacitor, we have only active power. We don't have a reactive power. And this P total will equal to the power of the loads, because when you add the capacitor, you're adding a negative reactive power, but you are not adding any real power. So the P total of the two loads, which is the Y load and the motor and the capacitor, will be equal to the summation of the two loads, 20.67 plus 9.953, and this will give me total of 30.623 kilowatt. So this is your P total. From this P total, this is equal to root 3 V line I line cosine theta. But cosine theta is equal to 1 because now the new power factor is unity. This is equal to 600. So from this, your new I line current is equal to 30.623 times 10 to the power 3 divided by root 3 times 600, and this will give me total current equal to 29.5 angle of 0. Draw a phasor diagram showing the line currents without the power factor correction and with the power factor correction. Now we have two sets of currents. So before we connect, we have before the current is 38.9 angle of minus 47. After, the current is 29.5 angle of 0. Of course, this current is basically plus minus 120. Now let me draw this, the phasor diagram. So we have this one here, here. Let me click different color. So let me do this for before. So this is before here, blue. So we'll have 38.9. So this is the current in phase A, IA. The angle here is minus 47. Then you will have the other current is minus 120 of that, which is minus, this is 47. Okay, so this is minus 167. So this is IB. This is minus 167. And finally, you will have IC, which is, you add plus 120, which is 73. So it will be something like this. This is IC. Now let's go and choose another color for after. So let me have this. So basically, this is for after. The current is less and angle 0. So this is basically, this is IA prime. And this is minus 120. This is IB prime. And finally, this is your IC prime. And this is the, what we call it, the phasor diagram of my system. So with this, we covered almost all important topic that is related to the three-phase system.